1. So we are talking about the laboratory that we did about the Siamese network. So let's have a recap about the Siamese network. Most neural networks answer, what is this? Example, is this a cat? Is this a dog? Is this a fake news article? A Siamese network answers a different questions. Are these two things are similar? That is the entire mindset shift. Instead of predicting a class directly, the network learns a distance relationships between inputs. So the core idea of a Siamese network is a Siamese network contains two or more inputs, the same encoder reused multiple times, a distance comparison between embeddings. The important part is the weights are shared. Both images pass through the exact same neural network. So we have the same encoder. So encoder for image 1, encoder for image 2. So they have the same. So they are not encoder 1, encoder 2. So the image or the process that we are taking is processed only in one encoder, because different encoders will produce incompatible feature spaces. And what is embedding? An embedding is a compressed feature representation. Example, signature image. We encode it by encoder and produce the values in the vector. So that vector is embedding contains of random values, or I mean the values that it's supposed to be to it. So the network learns similar images is they are embeddings close together, but the different images are embeddings far apart. The main goal is the network tries to create an embedding space like this. So let's say we have the real signatures of the same person in the embedding space or the feature space. So those real signatures of the same persons are close, tied together, but the forgery is far apart or far away from those region. So the distance is same person is small distance and the forgery is large distance. So let's use the case ones. We use is in the signature verification. The lab uses anchor, positive, negative. This is called triplet learning. So the triplet structure is the anchor is a reference signature, the positive is another real signature from same person, and negative is a fake signature. So the goal of training is the network wants the distance of the anchor and the positive to be small, and the distance of anchor and the negative is to be large. So yeah. So why traditional classification fails here? So a formal classifier will need person A, person B, and person C, but every new person will require retraining. Siamese networks instead learn what makes signatures looks alike, so they can generate to unseen people. So that is extremely powerful. And why shared weights matter? Suppose we use different encoders like encoder A and encoder B for those. Now embedding are inconsistent. One encoder might produce 1, 2, 3 and another negative 15, 19 and 0. So the distance becomes meaningless. Shared weights ensure that the same rules, same feature extraction, and same embedding space. So a dataset structure in our lab that we did is we organize data like in the folder we have the real and the fake that contains the images or the sample data. This enables dynamic triplet generation. Next is signature triplet dataset. This custom dataset generates triplets on the fly. Instead of storing every triplet manually, it randomly creates them. So important design is the dataset intentionally ignores the gate item and its argument index. Why? Because triplets are randomly sampled every time. So every epoch gets fresh combinations. This increases training diversity. So the training objective is the module, so PyTorch triplet margin loss. So if the distance of anchor and positive must be less than in the distance of anchor and negative by at least some margin. So mathematical intuition is the loss wants positive distance plus margin is less than negative distance. So if it's true, loss becomes near zero. If it falls, model gets penalized. And example, positive distance is 1.10, negative distance is 1.5, and the margin is 1. So check. Let's check is 1.2 plus 1, that is the margin, the positive is less than 1.5. So 2.2 is less than 1.5. That is false. Why is false? Because 2.2 is greater than 1.5. So penalty occurs. The network learns pull positive, so pull positive closer and push negatives farther. So your distance calculation, usually Euclidean distance, we measure it in the function of d, and its argument is x and y. This is basically multidimensional Pythagorean distance, exactly like what we realized earlier. So the encoder backbone is the Siamese network itself is flexible. We can plug in CNN, ResNet, EfficientNet. The encoder extracts features. The Siamese structure compares them. So here's the important insight. The Siamese network is not learning, this is John, but it is learning these two signatures appear written by same person. That distinction is crucial. So why this generalizes well? Because similarly, patterns transform. Example, slant, pressure, stroke curvature, and spacing. These are universal handwriting characteristics. So the model works even on unseen individuals. So here's a case too. We use the Siamese network to satellite change detection. Now, this is the same architecture we use. Instead of signatures, it is before, image, and after. So the goal is to detect environmental changes. The model compares embeddings. So if it is not changed, that is embedding close. If it is changed, then the embeddings is far. So here's the power lesson here. The same architecture, different domain. This is shows Siamese networks are highly reusable. So application include is face verification, plagiarism detection, recommendation systems, and anomaly detection, medical image comparison. Next is contrastive loss. For change detection, the lab switches to weighted contrastive loss instead of triplet loss. So the core contrastive logic is for similar pairs is to minimize distance. For similar or for the similar pairs, ensure distance exceeds margin. So the similar pair loss is if images should match, so L similar is d squared. Why we square the distance? Because closer distance is lower loss, but the farther distance is larger penalty. So here is the similar pair loss. For different images, use the max function. This matches in our understanding exactly. So let's say if distance is greater to the margin, that is no penalty. That's correct. But if the margin is equivalent to 2 and the distance is equivalent to 5, then if we subtract the 2 by 5, that is negative 3. But so the maximum between 0 and negative 3, that is 0. So not penalty because they are already far apart. So what is smart moves? So the model stop wasting effort separating pairs already sufficient distance. So training focuses only on problematic examples. So here is the embedding space. So the model does not directly classify, it builds geometric space. Think of it like coordinates. Example, same things cluster together, different things separate apart. So classification becomes just distance measurement. Next is thresholding. So what is this? After training, the model outputs distances, but we still need a decision rule. Example, the distance is less than threshold. That is same because there are no significant changes. But if the distance is greater than the threshold, so they are different because it means there are changes. So why threshold matters? If it is too low, many false negatives, and if it is too high, many false positives. So In the lab, we searches for the optimal threshold using the validation data. So next is two-step prediction strategy. The greenery detection system is interesting. So step 1 is Simon's model determines change or no change using the embedding distance. So the step 2 is if change exists, HSV greenery analysis determines positive vegetation increases, negative vegetation decrease. This is hybrid AI. So deep learning plus logical heuristic. So that's a very common in industry. So there's an important realization. The Simon's model never learned HSV rules. It independently learned visual change patterns from pixels. And the HSV logic is merely post processing. Why this architecture is so powerful? Because it separates feature learning from decision logic. This is modularity extremely valuable. That's the feature learning is the Siamese networks, but the decision logic is the HSV rules. So, summarize, here's the concepts we must stick. So, shared weight is the same encoder used. The embeddings is compressed learned feature vectors, and the distance learning is learning relationship instead of labels. Metric learning is the model learns a distance metric, and generalization works on unseen identities, and dynamic dataset generation is triplets generated randomly during training, and the threshold-based decision systems is distance converted into predictions. So, science network is essentially learning what makes two inputs belong together, not what class is this. So, we are making the two inputs um, belong in what region, and what are they belong. So the final here, like example in the final mental model is if we input two values like input A and input B, and the shared encoder process them both, and we embedded A, and the embedding B is having a distance, and we make a decision based on the dynamic dataset. I mean in the threshold based decision system. So the network learns the embedding space, distance performs the comparison, threshold performs the classification. That is a full Siamese pipeline.